A 4.60 kilogram block is attached to a second block, mass 3.30 kilograms. The first object is on a table, which has a kinetic coefficient of friction of 0.221, whereas the second block hangs freely from a frictionless pulley. The second block is pulled down by an applied force of magnitude 40 newtons. Determine the acceleration of the system and the tension in the cord. Okay, so the first step is to plot all forces acting on each mass. There exists a tension force in the cord. Now, whenever you have a cord, the tension force appears twice at both ends, since the cord tightens at both ends. So again, this is that same tension force, but it appears twice. Okay, next, we do have friction this time. So friction acts to the left if the block moves to the right. So the block will move to the right. Next, M1 is on a surface, so there's a normal force. So we have the normal force N. We have a weight 1 acting on the block. So this is W1, whereas the weight of block 2 will represent that as W2. So make sure you distinguish between the two masses. Now at that point we'd be done, but I still would like to draw my acceleration of my block 2. It goes down. And this is typically what the diagram looks like, but I threw in an additional force. There's some generic applied force acting on block 2. So that's just somebody pulling down on it. So I just added this extra force here. It's somebody pulling down on the block. Now the diagram is complete. So you simply apply Newton's second law to each block individually. So sum of all forces in X equals mass 1, acceleration in X. We have two forces acting horizontally on block 1, a T and an F. Now, F always has the set in stone formula. Mu times N is friction, and that still equals M1A. Next, usually I box this and call this equation 1, but for tension, I do like to isolate it right away. So I can add my mu N to the other side and label this equation 1. Perfect. So the recurring theme is that tension, notice how we couldn't just break down tension and express it as some formula. So the recurring theme is that tension has no set in stone formula. Same with normal force, and I always emphasize that. So now let's go off on a side track, a side note, and find normal force. Okay, so we apply Newton's second law in the y direction for block 1. Add together all forces in y, M1, AY. Now block 1 is not lifted vertically off the table. It doesn't move up and down. So the vertical acceleration is 0. And again, there's just a normal force and a weight. So N equals W1. So N equals M1G. That's equation 2. Finally, apply Newton's second law in the vertical direction to mass 2. Add together all forces for mass 2. Referencing the diagram, I see there's 3 vertical forces acting on mass 2, a positive T, a negative weight, and a negative force. So we have a positive T minus W2 minus F equals M2. Now, just keep in mind these subtle details, and this is why the notation actually does help us. Acceleration points down, so it's negative. So that's the purpose of this notation here. This little arrow serves as a reminder that you go back to the diagram and you verify the sign. You look back and see that A points down, so it's negative. Finally, we get T minus M2G minus F equals negative M2A. Isolate T, you'll get positive M2G minus M2A, and then positive F. So we add it to both sides. And that's equation 3. Perfect. So now, since equation 3 is isolated for tension, and equation 1 is isolated for tension, we will do the substitution method, but kind of in a fancier manner. Since both expressions are equal to T, they're equal to each other. So again, equation 1 said T equals mu times normal force, but normal force is M1G plus M1A. So that's what T equals for equation 1, whereas T equals M2G and so on for equation 3. Next, let's see. Well, M1 appears in both terms, so that usually is a sign, or it signifies that you should factor it out, but we're not interested in doing that. We want to collect all A's on the same side. So I'm going to keep my M1A, and I'll add M2A. But then I'm going to keep my right side and subtract away mu M1G, and I still have F. Now, A appears in both terms, so you factor it out. You get A times the sum of the masses. G appears in both terms. You can factor that out and save some time. So the right-hand side becomes G M2 minus mu M1. Finally, acceleration, divide both sides by M1 plus M2. So you have the entire right side. It's a lot of rewriting, but could have done it as 2 steps in one. Entire right-hand side and divide. And that's the acceleration. We can plug in the numbers. A would be, let's see, we could do our G, 9.81, and then it was times M2, 3.30, minus mu, 0.221 times m1 plus the force of 40 newtons, all divided by sum of the masses. Let's see what we get. The numerator becomes about 62.4 divided by the denominator. So that's 62.4 divided by 7.90. And we get about 7.90. Good. Oh yeah, because 7.90 times itself would give about, okay. Yeah, so that's just a coincidence that it happens to look the same as the denominator. So that's what you get for the acceleration, 7.90 meters per second squared. And then finally, what's the tension? Well, you can use either equation 1 or equation 3. So referencing back to equation 1, we said tension was mu times normal force, but normal force was m1g plus m1a. And this is the form we left it in. But again, to save time, I will factor out that m1 now. You don't have to do this step, but we can write this as m1 mu g plus a to save us some time. So m1 is 4.60 mu times g plus a, which was 7.90. Yeah, plus the 7.90. Perfect. So let's find out what this gives us. 0.221 times 9.81 plus 7.90 times 4.60. So finally, the tension force is 46.3 newtons. So that's how you'd calculate the acceleration and tension acting on the block for this system.